Welcome back to the lab. Today we're going to test our first prototype. We're going to figure out what works, what doesn't, and how we can fix it. Before we can get into all that, I need to set this down. You should enter your project for a chance to win our design sponsorship. Check this out. Maybe you want to control something connected to mains, but don't know how to do it safely. We can help with that. That's what this contest is all about. Okay, that sounds great. Here's how to enter. Tell us about yourself, tell us about your project, tell us how we can help. Best of luck. I hope you're as excited to work with me as I am to you. So thank you for watching EEforEveryone, and I cannot wait to hear about your next great project. Okay, all right, let's get this moving. We've got 120 volts to make. No time for standing around. No dilly-dallying. It's not beer o'clock, that's for sure. Yep, time to get to work. Oh, right, me, yeah. Yeah, let's get to work. So we started our first test with the end of assembly. We just finished building this board. Minimum voltage in, getting the DC set up, just really basic tests. But no sine wave? Why didn't we get a sine wave? Well, at any rate, we were able to test the hot swap controller and push-pull converter, so let's dive into those first, pushing the voltage ever closer to our set point of 250 volts. If something pops between 0 and 250, we know that something is up in our design.
Okay, now this was just too funny. What you can see on the screen right now is the power connected correctly. Looks great. Positive to positive, negative to negative. We're using a black and a white wire. I put white to ground because it's neutral, and why not? Let's confuse myself. And this is where my mental lobotomy happened. I wanted to set the current limit, so I shorted the two probes together, put them back, and oh, wait, these are in the same hands. That seems wrong. Let's flip them.
A reverse polarity protection implementation is another important addition to this UPS. I hope that I never really need to see the circuit work. There's nothing mechanically preventing me in a delirious stupor from connecting the battery terminals to this system backwards.
Couldn't have said it better myself.
Test at the smallest possible output voltage, 50 volts. From here we continued our testing at a couple different angles, and by a couple different angles, what I mean is progressively cranking on the feedback potentiometer. There's really only one way around it. We made sure to power cycle between every adjustment, and that was for one great reason. The potentiometers are on the high voltage side of our boundary, and while we were doing this, we did notice something bizarre during all these power cycles. There came a point where increasing the output voltage above a certain level would actually cause the hot swap controller to trip the current limit. That's weird, since we're using a 6 amp supply and the hot swap controller is supposed to have a limit of 50 amps. Add that to the list of things that we need to investigate in our more detailed testing. There was one particularly terrifying situation though, during all these tests. After we powered on the boost converter, I noticed that the DC output was actually 500 volts. What? The maximum possible should have been 350, and we were requesting 150. So that was a bit higher than what we designed for, and I believe that the hot swap controller that we're using actually caused the switch mode power supply controller to brown out, but it did this too soon after it first powered on, so it started up and reset right away. And that led to an internal latch up which forced the PWM controller to blindly output the maximum duty cycle. Whew! Talk about nasty! But thankfully, everything seemed okay here. No sparks, no explosions. Everything was fine, except for the fact that we were making 500 volts. Well, sorry. Little clarification here. It was okay until we tried to turn off the UPS. When, bang! 2 of our GAN FETs got obliterated. Literally blown in half, giant spark. Turns out our software had enable and disable confused for the inverter disable signal that goes to the FET drivers, which explains the lack of a sine wave. When we tried to power on the FET drivers outside of their rated specs, which actually, they weren't outside of their rated specs, but one of them still caused our transistors to shoot through. Of Okay, I got the LDO still there. Yeah, so I think everything should be fine. I should be able to power on again. I saw a spark about that big that looked like it was by the battery terminals, which is terrifying mind. Because that's a lot of voltage that would be jumping around. So we're just going to go ahead and safely turn this potentiometer all the way down. So that should make it spin around 50 volts. Powered on. And we're spitting out 63 volts. Okay, let's try to power down again. That's what's supposed to happen. And now if we look at the DC bus, I don't know how there was a spark that big and loud. Like, my ears were ringing. It was so loud. And yet somehow, now I reboot and everything's just fine. Oh, I love this project. Oh, I love this project. Well, let's be honest. We didn't really need those transistors anyways. Let's fix our firmware to make the sine wave actually come out and continue our testing on the half that works. So this damage, while bad, happened with a strange set of circumstances. First, the push-pull converter was fed from a dirty voltage rail. It wasn't a constant DC rail. This somehow caused the switch mode power supply controller to internally ignore the feedback network, so it seems like something about the way this is receiving power is not valid. The gate drivers were then enabled in this state, while an overvoltage fault was present. One thing led to another. Here we are. We have a couple of FETs blown in half. As long as we have a board that's half broken, but still mostly functional, we may as well continue to gather as much information as we can, right? I mean, we still do have half of an inverter and a push-pull converter, so let's try to figure out what's going on with this push-pull converter before we put another board at risk. We want to get our push-pull converter dialed in to the rated output voltage of 250 volts. First things first, we need to bypass the hot swap controller to prevent nuisance trips, like what we're seeing with the 6 amp current trip, from getting in the way of our testing. With this mitigated, let's proceed. No more software current limit, but who really needs current limits anyways? We have one on our DC supply and some fuses if things get out of hand. Now that we have that enable signal thing figured out, we can see some sweet sine wave action going on in the not exploded half of our inverter. However, the board is really struggling to get through the power on soft start sequence, which is weird since there's no load. Add that to the list, we need to check out the current monitoring on the inverter. This could be a situation where we have a constant defined incorrectly in our software. We'll see. Okay, so 250 volts DC on the boost converter, reliable power on. Let's see if we can recreate the latch up in our push-pull controller while the hot swap controller is bypassed. This should prevent the brownout situation we were seeing before. And let's do this by repeating what we did before. Let's just power cycle the UPS a bunch of times to further investigate the interplay between turn-on events, the inverter, and the push-pull converter. Seems like there might be some strange interactions going on here in the power-on sequence, which is not what we expected. Based on our calculations and what we've seen before, enabling all 3 of these at the same time, or in any order, should be fine. There should be no possible combination that would cause damage to any one of these 3 subsystems. But ignoring what we expect, let's just listen to what the circuit has to tell us. And 1 power cycle. And a current limit? Oh boy, that's not good. And still a current limit. Yep. Super not good. And yikes. Looks like we've got some debug to do. Seems like our journey through the debug, bring up, and testing of this board is going to be a little longer than we were originally planning. We seem to have found a bug in our push-pull converter, found a way to cause our inverter FETs to shoot through, and somehow managed to short out the power input to our UPS by power cycling the wrong way. Sounds like we have some big questions to answer, huh? Let's start with, why is our hot swap controller tripping at such low output currents? Why did our push-pull converter decide to output 500 volts instead of 150? And why is there now a short across the main power input of our UPS? The last one is, can we reliably depend on the isolated gate drivers to not blow up our inverter FETs? Why did one channel blow up and not the other? I'm sure that we'll have more questions to add to this list before our testing is complete. However, we are one critical step further in our project. We got a board, we built a board, we broke a board. That was fast. Time to investigate the weak points that we just found in our design, find some ways to work around them, and circle back with a second round of testing once we find some ways to mitigate the problems. If you like what you saw today, then subscribe to be notified of our future videos where we'll be debugging the failures that we found today and fixing them. Now, I think that bring-up testing is a heck of a lot of fun. It's like wrestling with physics while leveraging your keen observational skills. If you think so too, let me know by hitting the like button on this video, finding us on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching EE for Everyone, and thank you for staying till the end. Bye!